This is SpaceTime, Series 24, Episode 61. Coming up on SpaceTime. New evidence changing the way we think galaxies evolve. The most ancient spiral galaxy ever seen. And has NASA's Mars Curiosity rover found organic carbon-containing salts on the red planet? All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has shown that galaxies like the Milky Way evolve gradually, rather than through a series of violent collisions. The findings, reported in the astrophysical journal Letters, are forcing astronomers to re-evaluate their current hypotheses on galaxy formation and evolution. The results are based on the first detailed cross-sectional study of a spiral galaxy. The galaxy, UGC 10738, is located some 320 million light-years away and is broadly similar in its structure and appearance to that of the Milky Way. Importantly, the authors discover that UGC 10738 has very distinct thick and thin disks, similar to those we see in the Milky Way. When you look at the Milky Way side-on, rather than from above, it's impossible to make out the galaxy's majestic disk of spiral arms. Instead, side-on, the spiral arms look as flat as a pancake, with a central galactic bulge in the middle, looking like a peach in the middle of the pancake, to keep the analogy going. In 1983, astronomers discovered that the Milky Way's disk is actually composed of two very distinct populations of stars. There's an ancient thick disk component of older stars, which are relatively faint and not visible with the unaided eye. And then there's a younger thin disk component, which includes our Sun, by the way, and it's the one which dominates the night, with its carpet of glistening stars cascading across the sky. The thin disk is about 1,000 light-years thick and about 100,000 light-years in diameter, and runs through the middle of the thick disk in the same plane. Now, as the name suggests, the thick disk is much thicker, being several thousand light-years across. It's also much less densely populated with stars, and it's rotating more slowly around the galactic center than the thin disk, but its stars are moving far more rapidly vertically. As well as being kinematically distinct, the thick and thin disks also have very different stellar populations, with the thin disk stars generally being much younger and still forming today, compared to thick disk stars which were all formed more than 10 billion years ago. And of course the difference in age means they have different chemical compositions as well, with thick disk stars having between a tenth and half the metallicity of the Sun, while thin disk stars have between a third and 3 times the Sun's metallicity. Metallicity referring to the star's elements heavier than hydrogen and helium, the primary elements created in the Big Bang 13.82 billion years ago. Now, the important thing about all this is the double disk structure with very distinct populations of stars in thick and thin disks is actually incredibly difficult to replicate in computer simulations. It suggests that only about 1 in 20 galaxies superficially similar to the Milky Way have experienced a collision resulting in distinct thick and thin disks. Now, this doesn't mean galactic cannibalism doesn't happen. It is a fact that galaxies get bigger by merging with or consuming other galaxies. But it appears not to have a significant impact on a galaxy's structure or appearance. And that suggests that when they do merge, galaxies come together far less violently than we thought. One of the study's authors, Nicholas Scott from the University of Sydney, says the observations indicate that the Milky Way's thin and thick disks didn't come about because of a galactic mashup, but more a sort of default path of galaxy formation and evolution. Scott says the Milky Way's thin and thick disks were thought to have formed after a rare violent merger, and so probably wouldn't be found in other spiral galaxies. But he says the research now shows that's probably wrong, and it evolved naturally without catastrophic interventions, which means Milky Way-type galaxies are probably very common. The research also shows that UGC 10738, like the Milky Way, has a thick disk consisting mainly of ancient stars, identified by their low ratio of iron to hydrogen and helium. While, again like the Milky Way, its thin disk is composed mostly of more recent, younger stars, stars which have high metallicity. Although such disks have previously been observed in other galaxies, it was impossible to tell whether they hosted the same type of stellar distribution and therefore were similar in origins. The authors of this study solved the problem by using the multi-unit spectroscopic Explorer or MUSE spectrograph on the European Southern Observatory's Very Large Telescope in Chile. MUSE allowed them to observe UGC 10738 and determine the metal ratios of the stars in its thick and thin disks. Scott and colleagues found them to be very similar to those of the Milky Way Galaxy, with ancient stars in the thick disk and younger ones in the thin one. Scott says UGC 10738's edge-on orientation meant it was simple to see which types of stars were in each disk. The authors are now examining a further 19 similar spiral galaxies to see if the observations hold up. Scott says the findings so far are providing important insights into the formation and evolution of spiral galaxies.
So we set out to answer the question, is our galaxy normal effectively? Or maybe a more scientific way of putting that, is it common? And the way we chose to answer this question is by looking at other nearby galaxies to see how much they had in common in terms of their properties and structure with our galaxy. So we kind of narrowed things down to a small subset of galaxies just based on the basics, things like having roughly the same number of stars as our galaxy, being roughly the same size, the simple properties. And then we really looked into detail in these nearby galaxies. And the paper we published looks at just one of these galaxies, and we compare it in great detail to our own Milky Way, and we find out that there's kind of an almost exact match between the structures we see in our galaxy and the structures we see in this other galaxy.
So tell us about UGC 10738.
Yeah, so this is what we call a Milky Way-like galaxy. As I said, we picked things that were roughly the same mass as our galaxy, roughly the same size. This galaxy is just over 300 million light years away, which for astronomers is kind of nearby. Probably doesn't sound like it to most people, but us astronomers have funny notions of distance. And with it's definitely in the kind of well, maybe not quite in the local universe, but one suburb over, as far as astronomers would think. And we observed this with some telescopes in Chile, and in particular this instrument called MUSE, which lets us take very detailed, not just images, but also spectra of this galaxy.
This is part of the European Southern Observatory, which
that's right.
We're now a collaborator with, thanks to a recent agreement.
Yeah, it absolutely is. And the sort of having access to MUSE is what lets us do this. There's no other instrument on the planet that could have done these observations. So without this kind of access to the European telescopes, even though they're based in Chile, they're sort of European telescopes, then we wouldn't have been able to do this study at all.
And as you looked at this galaxy, you noticed the thin and thick disks. Tell me about these.
Yeah, that's right. So one of the kind of most recent discoveries about our own galaxy, maybe 30 years ago, say, is that we have these two distinct disk-like structures. Now, if you go outside and look up at the Milky Way, you'll be able to see it's kind of a long, thin strip of stars across the sky. And what you're seeing there is the thin disk of the Milky Way. And we know there's also a thick disk. You can't really see it with your naked eye, but with telescopes and kind of careful studies, astronomers found that there was this second disk-like structure, which is also sort of long, but not quite as long, and thin, but not quite as thin. So it's about 3 or 4 times thicker than the thin disk, which is why we give it the inventive name of the thick disk. And then what we did is we looked in these other galaxies for the same structure. The other thing about the thin and thick disk is they're not just sort of different in terms of their structure, but they also contain different stars. And that's what we were able to do for the first time with this external galaxy, see if we saw the same kinds of stars in the same sort of physical arrangement as we found in our own Milky Way. And that's exactly what we found.
And so this tells you what, knowing that this galaxy is very similar to the Milky Way in terms of its stellar structure?
Yeah, there's a few kind of interesting implications of this. For our own galaxy, it tells us about how we think these thin and thick disks might form. Sort of the oldest theory for how this might happen is something like 9 billion years ago. Sort of a medium-sized galaxy might have collided with our own galaxy and caused this disruption, caused kind of a pause in the formation of our galaxy, if you like. And before this point, it was forming the thick disk, then it had this pause, and then after that, it started forming the thin disk. If that were the case, then we would expect thin and thick disks to be really rare in the universe, that they would only happen when a galaxy had experienced this kind of merger at the right time. Now, but we found it in other galaxies. That really argues against this theory. If these thin and thick disk structures are common, then we need a much more sort of common way of forming them. And so that brings us to this sort of second theory that says thin and thick disks are kind of a natural process of the way we form galaxies, if you like. They just sort of happen and come about through the way we form stars. And even though it seems a little bit strange to have these two kind of structures with their different kinds of stars arranged differently, it turns out that with a kind of a more careful look at the theories of how galaxies formed, you can get the structure out of just kind of the default pathway, if you like.
So using this default pathway, does that mean that there's a huge cloud of gas and dust and it sort of gradually condenses 13 billion years ago to form a galaxy? Is that sort of the idea?
Yeah, that's right. And it's not quite a trick, but the subtlety here is that once you start forming stars, those stars after a little while start exploding. They go supernovae. And what we think happens for the first sort of couple of 100 million years, we get one type of supernova that comes from really massive stars. We call these type 2 supernovae. And they release a certain sort of signature of elements into the galaxy that then get recycled in future generations of stars. After about 200 million years, you end up using up all of these really massive stars. All those stars have gone bang, so there's no more of them to explode anymore. And then you get a different kind of supernovae that we call type 1As that are doing the enrichment from then on. And they have this different chemical signature. So it's really this transition from an early phase where you get these sort of massive stars exploding, one where it forms a thick disk, and then later on in the galaxy's life, you get a different kind of star exploding, and that gives you different chemical signature.
Now, this is separate from population 2 and 3 stars, I take it, or are we talking about?
Yes, that's right. Yeah, there are unfortunately similar naming conventions, but they're different. They're related. So population 3 stars were more massive, and we do expect them to have mostly gone into these more massive core collapse supernovae.
That would have been really early on. That would have been.
Yeah, that was very, very early on. So this is a little bit later in the galaxy's life.
Right.
The sort of the population 3 stuff is in the first, well inside the first billion years of the universe. The thick disk we think formed for maybe the first 3 or 4 billion years of the galaxy's life, something like that. Oh, yeah. So it's a little bit more extended.
So what does this do about the accretion theory? Because we can see star trails that clearly have different origins within our own galaxy and within other neighboring galaxies. We've seen them as well. So,
absolutely.
So obviously, you've then got to superimpose that galactic cannibalism on top of this more gentle evolutionary theory.
Yeah, that's right. So we absolutely think that still happens. Our observations don't change that at all. We know galaxies merge and grow through swallowing up other galaxies. I think what our results suggest is that part of the process isn't as important as we used to think. No matter about the sort of the details of that, this galaxy collided this one that was twice as big or half as big 5 billion or 7 billion years ago. I think what our results are saying is that those details don't really matter. They happen, sure, and we see the effects and they make little changes to the galaxies that they happen to, but the kind of the fundamental story, if you like, doesn't worry too much about those details. You're going to end up in the same place no matter whether you had that merger at that exact time or if you didn't have that exact event at that time.
I guess that's why we're not noticing Sagittarius dwarf crashing into us now.
Yeah, that's right. These are, that's a much smaller galaxy than our own, so it's perhaps not that surprising that these little things happening don't disturb things. Now, many of them happen, and, if you add up many small things, then you can certainly see a big change, but we don't think that, or at least this result is suggesting that in this particular respect, we're not seeing the effects of all those mergers. When you have a much bigger merger like the one we expect for Andromeda and the Milky Way in 3 or 4 billion years' time, then that'll definitely shake the galaxy up.
This has been a pretty stunning result in terms of understanding galactic evolution, hasn't it?
Yeah, I think so. There's been lots of sort of little hints, as I suggested. Sort of this alternate theory had been talked about a little bit, but hadn't got much traction. But it's kind of a couple of nice things have come together to really allow us to do this study. Firstly, we've got to know our own galaxy a lot better over the last couple of years. There's something called the Gaia satellite that's observed the locations of a billion stars, literally a billion stars in the Milky Way. And that's let us make our first kind of maps of the whole galaxy rather than just a little bit of it. And then it's this instrument Muse in particular that's let us kind of observe other galaxies in almost the level of detail we can observe our own. So it's really this, knowing our own galaxy better, knowing these other galaxies better, and then we can make this detailed comparison that we just hadn't been able to do before.
That's Dr. Nicholas Scott from Australia's ARC Centre of Excellence for All-Sky Astrophysics in 3 Dimensions, Astro 3D, and from the University of Sydney. This is SpaceTime. Still to come, the most ancient spiral galaxy ever seen, and scientists using NASA's Mars Curiosity rover think they may have found what appears to be organic carbon-containing salts on the red planet. All that and much more still to come on SpaceTime. Scientists have found what may be the earliest spiral galaxy ever seen, going back an amazing 12.4 billion years. A report of the journal Science says the discovery of a galaxy with a spiral structure at such an early stage in the evolution of the universe is an important step in the quest to determine how spiral galaxies, like our own Milky Way Galaxy for example, are formed. The discovery was made using ALMA, the Atacama Large Millimeter Submillimeter Array Radio Telescope in Chile. About 70% of all galaxies we see in the universe are spirals. However, the proportion of spiral galaxies tends to decline more and more as astronomers look further and further back in time. And that raises the question of when did spiral galaxies first begin to form, and just as importantly, why? Scientists with the National Astronomical Observatory of Japan noticed a galaxy called BRI 1335-0417 in the ALMA Science Archive. The strange-looking blob had been largely obscured by dust. But while the dust made it difficult to study in visible light, ALMA is able to peer through that dust and examine the galaxy at radio wavelengths. And lo and behold, the authors found it had a spiral structure, the earliest ever seen, extending out at least 15,000 light years from the galactic centre. They also found this galaxy had about the same mass as our own Milky Way Galaxy, but it appears to be much more compact, with just a third the diameter of the Milky Way. However, the authors admit that being so far away means they're not really able to detect the full extent of the galaxy's size. Still, regardless, it's a giant for its time. So the big question is, how did this galaxy obtain its spiral shape so early in cosmic history? Now, one possibility involves an interaction with a smaller galaxy. Remember, the majestic spiral structure we see in galaxies is thought to be caused by density waves passing through a galaxy's disk. And BRI 1335-0417 is actively forming stars. There's huge amounts of gas and dust streaming into the galaxy from possible collisions with smaller surrounding galaxies. Astronomers are also speculating about the galaxy's ultimate fate. With so much gas and dust streaming in, starbursts taking place all around, it could eventually transform from a spiral to an elliptical galaxy. That's if their hypothesis is correct. This is SpaceTime. Still to come, more possible organic compounds found on Mars. And much to the chagrin of astronomers everywhere, SpaceX launches its 1737th Starlink satellite. All that and much more still to come on SpaceTime. Scientists using NASA's Mars Curiosity rover have found what appear to be organic carbon-containing salts on the red planet. The findings, reported in the Journal of Geophysical Research Planets, could have important implications for the red planet's past habitability. Now, before we get too excited, it's important to point out that organic compounds and salts could have formed on Mars through geological processes. But the thing is, they could also be remnants of ancient microbial life. Besides adding more evidence to the idea that there once was organic matter on Mars, directly detecting organic salts would also support modern-day Martian habitability, given that on Earth, some organisms use organic salts, such as oxalates and acetates, for energy. The study's lead author James Lewis from NASA's Goddard Space Flight Center in Greenbelt, Maryland, says the discovery of concentrations of organic salts on Mars makes the location an ideal spot to drill deep below the surface where organic matter could be preserved. Lewis's lab experiments and analyses of data from SAM, the Sample Analysis at Mars Chemistry Laboratory instrument on board the Curiosity rover, indirectly point to the presence of organic salts. But the problem is, directly identifying them on Mars is actually quite hard to do with instruments like SAM. SAM works by heating Martian soil and rocks to release gases, and these gases then reveal the composition of these samples. The challenge is that heating organic salts produces only simple gases that could be released by other ingredients in the Martian soil. So, Lewis now wants to use Curiosity's chemistry and mineralogy instrument. It could detect certain types of organic salts, but again, there's a caveat. They need to be present in sufficiently large amounts. And the problem there is, the instrument hasn't yet found them. That could be because the levels are simply too low everywhere, or it could be because they're really not there. Finding organic molecules, or at least their organic salt remnants, is essential in NASA's search for life on other worlds. One of the big problems on Mars, of course, is the billions of years of radiation which has bombarded the red planet's surface and would have long irradiated or broken apart any organic matter there. Like an archaeologist digging up bits of ancient pottery, Curiosity collects Martian soil and rocks which may contain tiny chunks of organic compounds, and then SAM, or another instrument, needs to identify the chemical structure. Using data that Curiosity then sends to Earth, scientists like Lewis try to piece together these broken organic pieces, and then infer what types of larger molecules they may once have belonged to, and what those molecules could reveal about the ancient environment and the potential biology that was there. Since arriving in Gale Crater in 2012, NASA's six-wheeled Mars Curiosity rover has drilled into numerous rocks searching for organics, molecules containing carbon. Scientists using Curiosity's SAM instrument first detected ancient organic compounds preserved on Mars back in 2018. Jennifer Eigenbrot from NASA's Goddard Space Flight Center in Greenbelt, Maryland, led the team which made that discovery.
We want to know, has life ever existed on Mars? Do pockets of life persist on Mars today? NASA's approach to answering these questions is to break them down into smaller and smaller steps. First, we need to know if ancient Mars was habitable. Did it once have the right climate and the right chemistry to support life? The Curiosity rover is investigating these questions by looking for organic molecules containing carbon. Organic molecules are the backbone of all life on Earth, though they can also come from non-living sources. Today, the surface of Mars readily destroys organics, making them difficult to detect.
We are decelerating.
Curiosity landed in Gale Crater on an ancient lake bed. A few months after arrival, it drilled into sedimentary rocks and detected traces of organic molecules using an instrument called SAM. Now Curiosity is climbing the mound in the middle of Gale Crater, and SAM has made a subsequent detection of organics. This is exciting because it comes from rocks that are billions of years old. That means that the organic material within them is extremely ancient. Some of the organics that SAM has detected contain sulfur, likely introduced through geological processes. Sulfur can act as a preservative, binding organic molecules together to make them tougher and protecting them from oxidation. In fact, sulfur is the element that makes hair and fingernails tough, as well as vulcanized rubber. Martian sulfur has probably had a similar effect on these old organic molecules, helping to preserve them over geological timescales. SAM made detections by heating samples of crushed rock to very high temperatures, above 1,000 degrees Fahrenheit. This vaporized the samples and released several species of small hydrocarbons like benzene and propane. Because the hydrocarbons were released at such high temperatures, they may be the fragments of bigger, heavier molecules within the rock similar to kerogens. On Earth, kerogens are found in rocks like black shale and coal and are the products of ancient plant and bacteria. We don't know if the recently discovered organics on Mars are of biological origin, but it's exciting to find such old material preserved right at the surface. This finding is also encouraging for future exploration. In the distant past, Mars was much warmer and wetter than it is today. The rocks at Gale Crater tell us it was once an environment where life as we know it could have survived. The discovery of ancient organic molecules shows that another ingredient of life was present at that time, and it broadens our understanding of habitability of both ancient and modern Mars.
And since that first discovery of organic molecules, the search has been on to find more. And the key instrument for that is SAM. SAM works by heating samples to over 1,000 degrees Celsius, breaking molecules apart and releasing gases at specific temperatures which can be analysed and identified to determine the composition of the original rock or mineral. But there are lots of interactions taking place, making it difficult to draw specific conclusions. This report from NASA TV.
How do you know if there was once water on Mars? Or, for that matter, life? Obviously you can't tell just by looking at pictures of Mars, but scientists think the answer may lie hidden in tiny molecules in Martian soil. So, how do you take apart a molecule to see what's inside? Luckily, scientists have a tool to do just that. It's called a mass spectrometer, and it lets us take an extremely close look at whatever we're studying. And even though Mars immediately comes to mind, mass spectrometers are used in multiple NASA missions. They're also used in labs for hundreds of scientific purposes. But the important question is, how does it work? Today we'll be looking at a special kind of spectrometer called the quadrupole mass spectrometer. It's called this because of the 4 long poles that make up the center of the instrument. So say you have a sample that's been turned into a gas, and you want to find out if it contains certain things. The gas is sent into the mass spectrometer, first hitting a piece called the ion source. Here, a stream of electrons hits the molecule, breaking it into fragments and giving each fragment a charge. Next, the fragments enter what's called the analyzer. Here, they're separated based on their mass, and the analyzer is tuned so that only the fragments we want to see make it all the way through. Everything else flies off in a different direction. After this, the fragments hit what's called the detector, and scientists record the data. If you're looking for more than one kind, the analyzer can scan across a range of fragments, building up a record of not only what kind, but how many. Once you have these results, called a mass spectrum, you can verify that your sample in fact contains what you're looking for. And here, the real work begins. The mass spectrometer is a powerful tool, and by taking many samples, looking at the results, and studying what we find, scientists can work to discover not only the secrets of water and life on Mars, but also answers to bigger questions about the universe. And all by studying something as tiny as a molecule.
Here on Earth, Lewis and colleagues have analysed a range of organic salts mixed with inert silica powder in order to replicate Martian rocks. They've also investigated the impact of adding perchlorates to silicate mixtures. Perchlorates are salts containing chlorine and oxygen, and they're common on Mars. Scientists worry that these perchlorates could interfere with experiments seeking signs of organic matter. And it turned out to be a good call. They found perchlorates were affecting their experiments. But they also found that the results they collected from perchlorate-containing samples better matched the SAM data than when the perchlorates were absent. And that bolsters the likelihood that they have indeed found organic salts. This is SpaceTime. Still to come. SpaceX launches its 1,737th Starlink satellite, much to the chagrin of astronomers everywhere. And later in the science report, the World Health Organization admits that the real COVID-19 death toll could have already passed 8 million. All that and more coming up on SpaceTime. SpaceX has undertaken 2 more Starlink launches, carrying another 102 broadband satellites into orbit. Starlink 27 carried 52 Starlink satellites, as well as 2 rideshare payloads, a radar Earth imaging satellite for Capella Space, and an optical spectrum astronomy observation satellite, the Tyvak 130, for Tyvak nanosatellite systems. The mission from Space Launch Complex 39A at the Kennedy Space Center at the Cape Canaveral Space Force Station in Florida marked the 8th successful launch and recovery of the same Falcon 9 booster, which eventually landed on the drone ship Of Course I Still Love You, which had been pre-positioned some 680 kilometers downrange in the North Atlantic Ocean. And just 11 days later, the company launched its Starlink 28 mission, carrying another 60 Starlink satellites into orbit and bringing the total number of Starlink spacecraft now launched to 1,737. The mission from Space Launch Complex 40 at Cape Canaveral was only the second flight for this particular Falcon 9 booster, which then successfully returned to the surface, landing on the drone ship, just read the instructions, following the mission. Ultimately, SpaceX hopes to have some 42,000 Starlink satellites in their low Earth orbit constellation, providing global broadband satellite internet service. Each 260-kilogram satellite is equipped with Ku, Ka and E-band phased array antennas, as well as laser transponders and Hall effect thrusters. The ever-growing Starlink constellations are angering scientists because they interfere with important astronomical research, leaving bright streaks across optical images and affecting sensitive radio telescope observations. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. The World Health Organization has admitted for the first time that the true death toll from the COVID-19 pandemic could be somewhere between 6 and 8 million people, rather than the 3.5 million officially listed by the organization. The WHO's Assistant Director General Samira Asma confirmed the likely true death toll during a press conference looking at the latest data and analytics, which included both the number of deaths directly and indirectly attributed to COVID-19 since the virus first emerged in Wuhan, China. The new numbers were presented at the annual World Health Statistics Report, which estimated that the total number of deaths from the COVID-19 pandemic in 2020 was at least 3 million, or 1.2 million more than what was officially reported at the time. The UN agency's official figures estimate around 3.4 million people have died directly as a result of COVID-19 as of May 2021. Meanwhile, US President Joe Biden has ordered a new investigation into whether the COVID-19 coronavirus pandemic really did originate in nature or whether it leaked out of the Wuhan Institute of Virology. The White House ordered its 18 spy agencies to carry out the review following confirmation that 3 scientists from the Wuhan Institute of Virology were hospitalized on November 18, 2019 with COVID-19-like symptoms in what may well have been the very first cases of the deadly pandemic. Now, if you remember, we reported back on April 6, 2020, that's April 6 last year, that the first human case of COVID-19 was a 55-year-old man on November 17, 2019. The new confirmation of our original story was contained in a previously undisclosed United States intelligence report about bat virus gain-of-function experiments being undertaken at the Wuhan Institute of Virology, splicing and mutating different viruses together, including SARS-CoV-2, in order to create new viruses that had never previously existed in nature. That research was partially funded by the United States, which banned similar gain-of-function research in the US. Now, the November 2019 date's important because it coincides with the time frame most epidemiologists and virologists believe the SARS-CoV-2 virus behind the pandemic first began spreading through the central Chinese city of Wuhan. On the other hand, Beijing claims the first case of COVID-19 was a man who fell ill in late December 2019. The Chinese government didn't alert the World Health Organization of the outbreak until December 31st and didn't admit to human transmission of the virus until January 21st, 2020. That mid-November date also happens to be the time that Beijing ordered the Wuhan Institute of Virology to destroy thousands of pages of research documents and records covering more than 300 studies and undertake a major sterilization program of the entire facility. It was also around then when Beijing began banning people in Wuhan from traveling to other parts of China, while still allowing international travel from Wuhan to continue. And it was about then when Chinese companies were ordered by the Chinese Communist Party to start buying up all available supplies of antiviral drugs and ventilator machines, as well as gloves, masks, respirators and other personal protective equipment, effectively stripping entire countries of their supplies. Now, in response to the latest moves by Washington, Beijing has restated its earlier claims that the virus was brought into China by American troops. Of course, Beijing's also previously blamed the Italians for the virus, and more recently, they blamed Australia. A new study warns that the maximum sea level rise predicted by the most recent reports from the International Panel on Climate Change are likely to be too low. The findings by Danish and Norwegian researchers reporting in the journal Ocean Science are based on calculations of future sea level rise, based on actual observations of changing sea levels in the recent past, and compared with computer model-based predictions. The authors say the Intergovernmental Panel on Climate Change estimates are simply too conservative because their models have never been tested against past patterns of sea level rise in order to check that they're accurate. A new study warns that human-made greenhouse gases are causing the Earth's stratosphere to shrink. The findings, reported in the journal Environmental Research Letters, are based on satellite data and computer modelling. The stratosphere is the atmospheric layer stretching from between 20 and 60 kilometres above the Earth's surface. It's located directly above the troposphere. That's the atmospheric layer we live in, extending from the planet's surface up to around 20 kilometres. Earlier research had shown that the troposphere is expanding due to increased heat captured by growing concentrations of carbon dioxide. The new research shows that the troposphere expands and pushes into the stratosphere. Carbon dioxide then contaminates the stratosphere, cooling it down and causing a contracting effect. The research shows the stratosphere is already thinned by some 400 metres since the 1980s and could continue to shrink by up to a kilometre within the next 60 years. A new study has shown that there are roughly 50 billion birds in the world. The research by the University of New South Wales looked at some 9,700 known bird species ranging from eagles and sparrows through to emus and penguins. The findings, reported in the Proceedings of the National Academy of Sciences, use complicated algorithms based on actual sightings plugged into the eBird database. The report found that many iconic Australian bird species are numbered in the millions, including some 19 million rainbow lorikeets, 10 million sulphur-crested cockatoos, and 3.4 million kookaburras. But sadly, other species remain incredibly endangered, such as the rare black-breasted button quail, of which there are just 100 individuals left. It seems the world's most common birds are house sparrows, of which there are some 1.6 billion members. They're followed by European starlings with 1.3 billion, ring-billed gulls with 1.2 billion, and barn swallows with 1.1 billion members. The study's dataset includes some 92% of all known bird species currently alive, with the remaining 8% being so rare, reliable data is lacking. From BBC journalists using forged documents to the ABC's left leanings and CNN Middle East reporters tweeting that Hitler was right, once highly reputable news services can simply no longer be trusted to give you the truth. In the new news media environment, journalists are pushing their own beliefs rather than providing fair and balanced reporting. Facts are drowned out by opinion, and getting the real story is harder than ever. So, Tim Mendham from Australian Skeptics has come up with some tips to help you be sure that at least the science news you're getting is real.
Suggestions have been put forward that the few little tick boxes you can have to see if something is dodgy, right? Dodgy in a science term. The first one is that has it been peer reviewed? In other words, have other scientists looked at it and sort of saying, no, that's rubbish, we're going to tear it apart. That's the way peer review is actually when you put your article in your paper in, it's independently assessed by other scientists who don't know who you are, and they say, yeah, that's okay, or yeah, this is a bit dodgy, or what does this mean? Go back and do it again. It's not perfect, unfortunately, peir review.
It's the best
not perfect by any means.
But it's amazing how few people know about, in the general public, how few people know about peer review, and yet it's the most important thing. Do other scientists who are experts in this field agree with what you've concluded?
Yes.
So important.
But I've seen enough PhDs and things to get through the mill, and that should never have been done. They're full of errors. And unfortunately, that does happen, and a lot of people who are doing the peer review, it's supposed to be part of their job anyway, senior academics and people like that, but they just churn through them and they sort of say, how closely they read or check the tables or the graphs or the photos or the conclusions, etc., see if they work. Anyway, but you're right, it is better than nothing by a long way. And then, of course, you have once something's been published, which might take a few months before it gets published, you then have the general science community can look at what you've said and they can tear it apart. That's not peer review as such, but it's actually peer assessment in a way. So that works as well. So the world of science is a rough and tumble where to get your idea accepted you have to really go through a lot of hoops, which is good, the way it should be. Anyway, that's one thing. If your claim is not being peer reviewed in any way, and if it just sort of, as I heard one person who was making claims about particular medicine things saying, my uncle read it. he agreed it was good. So yeah, okay, come back later when you get someone here who's
If it's not
a
peer
little less.
reviewed, it didn't happen. It's that simple.
The next thing is to look for the blind spots in your own blind spots in actually how you read a report, how you look at a particular claim. Obviously, the researchers can be biased, that happens, but the reader can also be biased, yourself in the way you see it. I don't agree with this particular philosophy, so therefore anyone who espouses it is wrong, no matter what they say, no matter what the evidence. So that's another thing to watch out for. A lot of it's called confirmation bias, which is you pick out the bits that work for you and you ignore the bits that disagree with you. A self-perpetuating agreement. There's often a thing about correlation and causation. Just because two things happen at the same time doesn't mean one causes the other. It's amazing how often people make that suggestion, and that's very true of vaccines and unfortunate occurrences, which is putting it mildly in some cases. Therefore, one causes the other, and it doesn't necessarily happen. Especially the cases of MMR vaccine causing autism, because you basically gave the MMR vaccine at about the same time when autism became apparent, and therefore they were suggesting that one causes the other where there's no evidence for that at all. So that's the correlation is not causation. So you have to watch out for that sort of logic, poor logic.
Yeah, correlation, causation, and confirmation bias. They're both very human traits, which were probably really important back in the days when we were hunter-gatherers. They helped us find which trees to look for the best fruits and where the sweetest water was and things like this.
Yeah, but being hit by a lightning bolt does not mean God exists. So that's the issue that someone said that there's a wonderful site which looks at dodgy correlations, and they had this graph showing the frequency of things happening. And one was the number of films released by Nicolas Cage is in exact proportion to the number of people who were strangled by their own bedclothes.
Yes.
And that's the correlation causation thing. I don't think one caused the other, but never mind. We've discussed this before too. The number of subjects and who was, when you're doing random surveys and controlled trials and things like that, unfortunately, most times you're using people, and people are sort of very inconsistent beings. So that's why you have to have a lot of people when you're doing a trial, a controlled trial. The more people, the better. And also you have to make sure the trials are double-blinded, whether the subjects and the practitioners don't know which one is, say, getting a real medicine and which one's getting a placebo. Someone else has to manage that so you don't get built-in biases and built-in controls, also built-in suggestions that people might be making. Nudge, nudge, you've got the good one, that sort of thing. So you have to watch out for the nature of studies and especially the people involved.
This is why phase 3 trials are so important. You need at least 30,000 people in a phase 3 trial thereabouts. Yeah. That's why they're so important in terms of making sure any medication is worthwhile taking, because that's when you start to get a decent percentage of the population. Still not getting all the population. That would require a trial of 7 billion people.
By which stage it's not a trial anymore.
No.
And the next tip is about what you call false balance. A lot of media go in for this. They say, if I'm going to interview someone pro a particular thing, I've got to also interview someone who's against it, and that's not true. A lot of people used to claim that was one of the rules on the ABC rules for journalists. It's actually not. There is no force to interview someone on the opposing side, especially if the opposing side is speaking a lot of rubbish. If you're talking to an astronomer, as I'm sure you do all the time, you don't also talk to an astrologer.
No, because the science is proven. There's no need to talk to an astrologer because that's not science, and that's been disproven. So the facts are there. All we'd be doing would be being repetitive about stuff we already know.
Same thing applies to anti-vaxxers. People doing stories on vaccination kept having anti-vax campaigners on as if their views were equivalent to someone who knows what they're talking about. And they weren't. And gradually the media sort of realised we don't have to interview these rabid anti-vaxxers just to make our story look fair, because it's interviewing someone who's not fair in themselves. So it's a thing that media have to watch out for, and what people who are looking at media stories have to watch out for, that they're not equivalent. Both sides are not equal necessarily. And the last thing is making sure that the reporting is clear and honest, and that's the hard one to gauge. How do you know who's being honest, etc.? But there's certainly a lot of people out there in the media, experts, who are particularly dodgy in some of the advice they give, unfortunately. So you have to watch out. So there's a whole range of different things to watch out for when you see a report. It's basically generally applying critical thinking.
That's Tim Mendham from Australian Skeptics. That's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies. or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.